layer, you're probably seeing neurons that are a function of the entire image. And so you'd get just these kinds of things, I assume. And then for layer 3, 2, 1, we have again, yeah, it's self-explanatory. Looks fun.
So that's like derivative. I mean, that's for the score, like to optimize the score of a particular class, or
that's right. So this is achieved by optimization. So these are the images that maximally activate some unit in the neural net.
In the last like, score.
Yeah. Not on the last layer for score, for any arbitrary in between layer of content. Okay. That's right. And so this is achieved by optimization. So forward, backward, update image, and do this many times, and these things just come out. Whereas before we were doing just a single backward in the decomp approach. Okay, another kinds of fun questions we can look into is where are we? Another kinds of fun questions we can look into is the following question. How much information is there basically in these codes? So when we forward the convolutional network through, we get some code here, the FC7 features, just before the classifier, and that's 4,096 numbers that form a summary of the image. And the question is, can we actually invert the image just given the code? Okay, so you might imagine that this might actually have some potential repercussions for privacy-aware applications maybe, because maybe some companies might try to only store the features, not the raw images. And the question is, like, can you actually invert that? And so the way this optimization would look like is we're given a particular feature, and we'll formulate it as just we want to minimize, we want to find an image that best matches that feature, say just as a regression. So we want to match that code and subject to a regularizer on the image. And so instead of maximizing any arbitrary feature, we just want to have a specific feature, and we want to exactly match it in every single dimension. And so when you run this optimization on the image, you get something that looks like this. This is the original image. So we forwarded it through ComNet, and we got our code. And then here we are trying to invert it from just that code, just from those 4,000 numbers. And so you can see that some of the structure, this is from different initializations, I believe. Some of those structures are still visible. And so that's roughly gives you a hint of just how much information is present in there. You can actually not do the reconstruction at just the final code layer. You can do it anywhere in the ComNet. So for example, on the pool 5 layer, which is slightly lower down the network, the pool 5 layer has much more spatial information than the final code layer. And so you can actually do a bit better job of reconstructing. So in this case, for example, the position of that bird is actually relatively recoverable just from the code. So quite a lot of information packed in there. You can also look at a single image and look at where we try to recover it from. So you can see that in the end, there's very abstract recoveries. Doesn't work super well. But as you go down, you have many more activations in the ComNet. And when you're very close to the image, you can actually do a very good job of reconstructing. So this gives you a sense of exactly how much information is thrown out by the ComNet as it's doing this forward pass, roughly. Just one more example of this. Say this is a flamingo image. Again, the same thing. As you go lower down the ComNet, you end up with more and more precise predictions. Okay, so we looked at maximizing activations. We looked at segmentation. We looked at matching a particular code. So we're now going to go into some other, any questions anymore about matching a code? Okay. So I'm going to go into Deep Dream. So Deep Dream, which I briefly flashed a few lectures ago, you can get really funky images. And as you might imagine by now, this is all done in the same process. We have an optimization process over the image, trying to achieve some kind of a loss in the ComNet. So what is the loss is really the question, because the process I think you already have a very good idea about. And so if you go into the GitHub page that Google released with Deep Dream, it's basically one IPython notebook, and there's literally, I think, like 100 lines of code in total. And so that's all of Deep Dream. It's a very simple process. In fact, I kind of took out a crop here, and this is the core of Deep Dream. And so the way this will work, and you can, if you're good at reading this, then you can see what Deep Dream is doing, but I'm going to go through it piece by piece. But this is a make step function here that you have a current image, and make step will be called repeatedly as we optimize. So every single make step call does a small update to the image. And notice that the input to make step is also this variable called end, which is a string denoting exactly what layer we want to dream at. And so basically, we can dream at any layers in the ComNet. And this is an inception network. And one of the inception layers is called inception, 4C. So that's where we might want to dream, for example. And the way this will work is, this is some boilerplate stuff here. And look here, we're doing net.forward. Then we're calling objective. and then we're doing backward and then update. So just to highlight some of the parts here, there's a bit of a jittering regularizer here that I don't want you to worry about too much right now. But the important part is this net.forward, what we're doing is we're forwarding the network, then we're calling the objective on DST, which is the layer at which we want to dream. And what's happening there is that DST is a blob in Caffe. This is Python wrapper around Caffe. And these blobs have two fields. They have a diff field and a data field. And the data field holds the raw activations, and the diff field holds the gradients. And so you can see that what the objective is doing is we forwarded the network up to some point, and now we're setting the gradients to equal the activations. And then we're doing backward from that point, back to the image. And then we're scaling the gradient on the image by some, we're normalizing the gradient and doing an update. And this is just clipping and stuff like that. So really what deep dreaming is doing here is, if you read into what's happening, is you have a ComNet, you pass the image through to some layer where you want to dream. And so you pass it through until then, and then the gradients at that point become exactly identical to the activations at that point, and then you backprop to the image. Okay, so intuitively in English, what is that doing? And this is always, you always dream, by the way, I should say, after ReLU units. So these activations are always zero cropped. So these are ReLU activations. So what is Deep Dream doing? Go ahead.
You're kind of amplifying the features that maximally activated the network.
You're amplifying the features that maximally activated in the network. Yeah, okay. I think that's that's very well said. So if you have so you have a collection of ReLU units in the forward pass, and this is some of them activated more than others. And now remember, like when we're computing the influence of any arbitrary piece of image on any arbitrary unit, we're kind of like setting the gradient to be like 1.00. But here we're setting the gradient to be the activations. So basically we're trying to find the image update that would boost any of the existing activations after the ReLU unit. So whatever we received as the activations, we're trying to boost all of it at the same time. So the way this will work is, if you take, for example, you get it to look at clouds, and you end up with this weird optimization that gives you all these little things. And so the clouds, basically, think about the ComNet looking at the clouds. There might be some, say, a dog-like detector that detects dogs normally. And if that dog detector thinks that this looks a bit like a dog face, just a tiny bit, then there will be some activation there. And then in the gradient signal, we're going to say, OK, we want to boost the activation of that dog feature. And so once we do a backward pass, we are finding on the image, how do we change the image so that that becomes more of a dog? So whatever activated just becomes boosted. And so we keep repeating this over and over again. And so we keep plugging this into Deep Dream, and this dog just becomes more dog-like over time, and the ComNet convinces itself that there's just like dogs or whatever else everywhere. Because it just keeps refining the image. Whatever activates, it just wants it to activate more. Okay, so that's roughly what Deep Dream is doing, and then you end up with all kinds of funny shapes like Admiral. This is from the Google post. They call them the pig snail, the camel bird, the dogfish. You just get all kinds of funky things. And intuitively, the reason you get dogs and fishes and so on is just, this was all trained on ImageNet, so there's a huge amount of dogs and in general like animals, so we have lots of dog features. So these ComNets are always very happy to detect dogs. And then if you show them anything dog-like, they'll just fire, and then they'll get boosted, and then you get dogs everywhere. We can also deep dream, as I mentioned, on any arbitrary layer of the ComNet. If you deep dream slightly lower, then those features are not about dogs or anything like that. They're detecting some weird shapes and patterns, right? So those features will kind of, be detecting those kinds of features, and that's what you'll end up reflected in the pictures. So yeah, that's basically how Deep Dream works. I should mention that this code snippet is really just about the core of it. There's one more code snippet that actually applies this on different octaves of the image, so for different scales, and there's a bit more to it. And this jittering is actually kind of important. And so there's some subtleties to it, but basically that's what Deep Dream is doing. And now we're going to look at some funny videos, because this is the best part. So so someone was running Deep Dream on video, but they were doing this optical flow smoothing, where they were trying to ensure consistency from frame to frame. So I don't know, it's just the most trippy video I'm aware of. Okay, I think you guys, it's a pretty long video, but I think you get the idea, so we're going to stop it here. I can show you one more here. This is deep dreaming. This is also a video from some movie that I haven't seen, but it's something about drugs, and so this is appropriate. And
65, the great San Francisco acid wave.
Acid wave. So.
I recall one night in a place called the Matrix.
And so here they do it frame by frame. I don't think they do some smoothing in this case.
There I am.
And I'll just forward. Maybe there's some. Okay. So. Okay, so you get the idea. So that's deep dream. So again, it's just optimization over the image. Go ahead.
What if you did the opposite? So instead of amplifying those signals, you reduce the effect of them?
So you want to instead reduce the signals of whatever activated. I have no idea what would happen, but you're very welcome to try it for a project or something like that. Okay. So we're going to another. Sorry, go ahead.
So what were you saying about the reason for all the dogs?
Oh, the dogs, like where they come from?
Yeah.
It's just there are so many features in the ComNet that really care about dogs because there's so many of them in ImageNet data that a large fraction of the ComNet features just really like dogs and have lots of features about dogs because you need to differentiate between them in the ImageNet data set.
The problem, so for ImageNet, there's 1,000 classes, and 200 of those are dogs.
Because the source of the image that people love dogs, so they upload.
I don't know exactly how that came about.
Well, the reasoning behind that is that sometimes we care not just about classifying broad categories, but they wanted to study the ability to classify within like very fine-grained categories that are very close to each other. So that's the reasoning why there are so many different types of dogs in ImageNet.
Yeah, you want to have both like broad categories and also fine-grained recognition in between, and you want to kind of test both. Okay. The next kind of, so we saw some applications. Okay, go ahead.
Yeah, so when you say that you're dreaming from layer X, you're picking a neuron from layer X and then pushing back, right?
Yeah, so when we're dreaming, so ComNet has all these layers. So when we're dreaming at layer X, we only forward up to X. And then at that point, all of the neurons, whichever one's activated, we are going to set the gradient. We will want to boost all of them at the same time. Yeah. So we're going to another fun application of optimizing over the image with ComNets, and that is neural style that some of you may have also seen. This was a paper that came out over the summer and had some really interesting, amazing results. So basically, you can take an original image and you can paint it in a style of something automatically. So for example, here I took a picture of Gandalf and Picasso painting, and I can actually optimize to get a Gandalf Picasso picture. So this is Gandalf in a style of Picasso. And this is actually achieved with optimization on the raw image with ComNets, which is amazing. Here are some more examples. So this is me as a Van Gogh style, Starry Night. This is my Picasso Gandalf. These are just randomly grabbed yesterday from a website that allows you to apply neural style to your own images. It's called deepart.io. And so you can create really like amazing looking pictures. We're going to go into how this works, and I still cannot believe that it works this well, basically. It's something very magical is going on. So let's see how neural style works. It's also a simple idea kind of as like deep dream. So what we're going to do with neural style is the following. We have two images in the input. We have a content image and a style image. And we want to transfer that style onto the content image, okay? So we have content and style images. What we'll do is we'll pass both of them through a ComNet. So first we'll take the content image and we'll pass it through a ComNet. And we are going to record all the raw activations in the ComNet. So for example, in VGGNet, there's a layer that might have this activation size. We're just going to store those raw activations. Very simple so far. And we're going to say that these raw activations basically kind of correspond to the content of the image. That's how we're going to call it. These raw activations kind of correspond to the content. Now, to extract the style, what we're going to do is we're going to take the style image, pass it again through the ComNet. But instead of keeping track of the raw activations, what these authors of this paper found was that actually a very nice kind of statistic of the style is not in the raw activations, but in their pairwise statistics. So what we're going to do is we're going to form all these outer products of all these basically covariance matrices that are spatially invariant in the ComNet. So for example, I have to draw this out because it's kind of confusing. We have a 224 by 224 by 64 volume in the first layer of a COMNet of VGGNet, say. Okay, so 64 filter activations at all these different locations. And then there's basically 224 by 224 what I'll call fibers. So these are 64-dimensional fibers of activations. And what we want as a statistic of the style of this image is this 64 by 64 matrix of all the outer products of all the fibers in this volume. So we take all the fibers here, we take outer products, and we sum it all up to get a single 64 by 64 matrix of these basically covariances, or gram matrices as they're called, of these activations. Another way to look at it is that we're going to take this volume, we're going to reshape it to be one matrix of 64 by 224 times 224. And so this is a very long matrix here, and we call this matrix V. And then the gray matrix is just V transpose V, so all the outer products. All the outer products added up. And so it's just keeping track of how often each pair of features fires together as you pipe this through the volume. So it's kind of looking at statistics of what features like to fire together across spatially the image. So all the outer products summed up across all spatial locations, okay, the gram matrix. And we are actually going to construct this not only at the first conv location, but at all the other conv volumes throughout. And then what we're doing when we're doing optimization for neural style is notice that this gram matrix construction is just outer products of all these fibers. That's a perfectly differentiable operation, right? And so our loss here will consist of two terms, a content loss and a style loss. So again, we start off with, say, a random image, or you can initialize at the content image. But we start off the initialization somewhere, and then we're going forward and backward to optimize over that image. And the loss is that we want the content to match the content image, and we want the style statistics to match the style statistics of the style image. And so all the activations throughout should match the content activations. So the activation should be the same like L2 sense. And all the gram matrices should also match. So all the pairwise statistics are from the style, and all the actual activations are from the content. And so these two guys are basically fighting it out in how they give rise to the backward pass of this image. And so in practice, I think actually we use only a single content layer. We only use like the 5th layer or something like that of content, and we use many more style layers. So we apply, I think, the style loss on multiple layers, and we apply content on only one layer. If you wanted to play with this, by the way, I forgot to mention that Justin actually has a very good implementation in Torch of neural style that is very popular, and it's on this URL. So you can see the implementation in Torch and see exactly how this can be implemented. But the rough idea is, just as with Deep Dream, just as with all the other visualizations we've seen before, we're optimizing over the image subject to some loss. In this case, the loss is that the activations at some layer should match the activations here. So we want something that gives you activations of similar to what you had when you passed Gandalf through, but we want these pairwise feature activations to match what you have when you pass Picasso through. And that turns out to create these kinds of images. I don't have a very good explanation of exactly how this happens. I still think it's kind of magic, and so I'm not sure exactly how this can possibly work. So I can't explain it any better than that, except for just like showing you the math. So yeah, that's StyleNet. It's kind of unsatisfying because I think it's confusing. But anyways, any questions about StyleNet, maybe? Good?
The V transpose V matrix,
yeah.
Couldn't we see it as some kind of like orthogonal projection on the style instead of the pairwise?
Could you interpret the V transpose V as some kind of a projection? I'm not sure if I'm fully seeing that. It's kind of like we take all these fibers and we stack them as columns, and then when we do this giant outer product of this times S transpose, we end up with a 64 by 64 matrix. And I think it's just a matrix of how often each the features across this depth like to fire together. And that's all summarized in this matrix, which will be, I think, symmetric. Yeah, so it's a symmetric matrix, and it just stores what neurons like to fire together. And that's what we're optimizing for with style. So in here, when we're actually optimizing over this COMNet, we'd like to have the same kind of pairwise statistics, but we'd like to have the raw activations of that. Yeah.
So what if we only use a style loss?
What if we only use a style loss? then you end up with kind of mixed up Picasso painting, I think.
So it is like kind of regularization?
Yeah, so you're asking, what if we only use this loss here for style? You basically will end up with a permuted Picasso. I've tried this out, and you'll end up with this image. It will look like a Picasso painting, but it will be completely permuted because all the spatial information is like not reconstructed exactly well, I think. It's mostly like the style stuff just tells you about the kinds of strokes that you have. Like say, for example, here in the Van Gogh, like these brush strokes are just perfectly summarized, and the content part kind of gives you the more global layout somehow. So. Yeah, like a texture is better stored in these pairwise activations is kind of like the point there. Yep?
I think your microphone may have turned off.
My microphone for the class? It was 1 bar, so that could be why. When did this happen? Just now? Yeah, it's turned off. Ugh. Okay.
There's actually a fun thing about neural style. You can, there's actually not, like the gram matrix isn't totally a special thing. Like what you really want is just some statistic of the activations that is spatially invariant. So the gram matrix is this like one statistic you might imagine that's really easy to implement. Another thing you can do is just take the mean feature activation across space, right? So instead of like a 64 by 64 matrix, you just get a vector of length 64 that tells you the mean activation for each feature map. And this actually does something, surprisingly, as well. So I'm not like, there's this interpretation of the gram matrix as sort of having this pairwise interaction between features, but I'm not totally sure that that's exactly what is making it work.
Yeah, it's a good point. I think, so this is a paper from the summer, so I think a lot of people are still trying to figure out exactly what's going on here. And so, Justin, you're pointing out that if you just take a mean over here, yeah, like the important part is actually the spatial invariant kind of part of it, not maybe. Yeah.
There's actually another paper that came out on arXiv maybe 2 weeks ago that uses a Markov random field to measure these interactions rather than this gram matrix. And they have some results that look really crazy, but it's like 10 times slower. So I tried it out, and it took a long time, even on a really good GPU.
Yeah. Another point I'd like to make, actually, by the way, I thought of is this is best optimized with LBFGS because we don't have a huge data set. And so everything fits in memory, and it's just a nice optimization here problem with a single image that we're backpropping through. So this is a very nice kind of use case for LBFGS. So the second order stuff works much better here than I think Atom and so on. So this is an example of where LBFGS would be very useful. Okay, so we'll get into the last part here, which is also very interesting and kind of confusing. And so the question is, we saw all these optimizations over the image. We can do lots of arbitrary stuff. So one question you might have is, can we use this optimization process to fool COMNETs? Spoiler alert, we can, and I mean it in the following way. What we'll do, and these are experiments from 2013 now by Christian Segedi et al. And what they did here is they took an image, say of this school bus, and then basically everything is differentiable. So we can ask for the gradient on that image for making, like for the ostrich class. So basically, ostrich class, so we forward the image, we set all the gradients to be 0 except for ostrich, where we set 1, and then we do backward pass. We get a gradient of what to change in the image to make that more ostrich-like. And what you'd hope to see is, as we run this optimization, you'd hope that this bus turns into an ostrich over time, but that is not, in fact, what happens. What happens is, somewhat depressingly, that it turns out that the distortion you need to actually get a very confident ostrich out of that image is this. And this is a very likely ostrich, but to you and I, it looks just like a bus. So that's kind of confusing. And so you can turn anything into an ostrich. You can turn, and actually anything, it's not even just about ostrich. You can turn anything into anything, and you need only depressingly small changes. So that's kind of weird, what is going on. So we're going to go over why this happens. You can also not just do it from the random image, you can do it from random noise. So we can start off with noise, and we can ask to change the image such that we get a robin or a cheetah or something with very high confidences. We can create these arbitrary images that basically the COMNET things are of this class. We can also use some more crazy, I think this is something genetic, something. But basically weird statistical patterns here that give you electric guitar or baseball with very high confidences. Okay? So that's kind of weird. I'd like to point out before we dive into exactly what's going on here that these kinds of results are actually not super new to computer vision. There are some papers, for example, from 2011 where you had similar kind of depressing results. Well, for example, they had two images here, and they found that they could change one image into an image that looks to us very similar. But in fact, these hog representations that we really liked to extract before ComNets came about, they are in fact identical for these two images, even though this image is clearly, they look very similar, but their hog representation, the feature representation is identical. So there were a few papers that were trying to study exactly what's going on with these, as we call, adversarial examples. One of the better papers on this topic was explaining and harnessing adversarial examples from last year by Ian Goodfellow, John Schlenz, and Christian Segedi. And they actually concluded from a whole bunch of experiments, and I encourage you to read through this paper, that actually the primary cause of this vulnerability is the linear nature of the functions that we're using in the forward pass. And we'll unpack this over time, I think by the end of this lecture, hopefully. But just the intuition I'd like to give you is the following. Images are super high dimensional objects, right? Lots of pixels, so like 150,000 dimensional space or something like that. And the real images that we actually train on, they have special statistical structure and they're constrained to a tiny manifold of this space. And we're training ComNets on this, and those ComNets work extremely well on that tiny manifold where the statistics of the images are image-like. But we're putting these linear functions on top of it, and we're correctly classifying that tiny submanifold, but outside of that manifold, we're kind of casting these shadows of complete randomness and chaos because we haven't trained there. What I mean by that is, suppose here we have a simple example, and I tried to classify this with a two-layer net, and you can see that around the data points, we're classifying them correctly, but look at what I call shadows. These are linear functions that are generalizing in a very funny way outside of the data manifold. So we are casting these linear, weird shadows outside of the data manifold. Like all bets are out. We haven't trained there. We haven't imposed anything there. And so arbitrary things happen outside of your data manifold. So anytime so that's something to keep in mind. And imagine this not in the space of 2 dimensions. Imagine it in a space of 150,000 dimensions, and how these shadows, as I like to call them, interact in very funny ways. So let's see a concrete example of just exactly how this linear nature might be a problem and what might be going on. We'll work with a specific case of logistic regression. So we're now in a case of just very simple logistic regression in small space. So we'll be doing W transpose X plus B, where X is, say, like 10-dimensional in this example we're about to go into. W is a small 10-dimensional vector, and B is a bias. And in logistic regression, we are putting that through a sigmoid. So this is the raw score we're putting through a sigmoid. And we're interpreting the output of that sigmoid as the probability that this input X is of class 1. Okay, that's what this says. So basically, we're computing a score here from the linear classifier, and then we're interpreting this to be class 1 if the score is greater than 0, or equivalently, if what comes out of the sigmoid is greater than 0.5, because that's indicating that the probability of 1 is greater than 50%. So that's the setup for logistic regression. And now we're going to go into a specific example here where we have some example X, and we have some weights W. And we plug this into our classifier, and we're going to compute W transpose X plus B. I guess we don't have a bias in this particular case. But we're going to compute W transpose X, which is really just 2 times -1 plus -1 times -1 times 3 times 1, and so on, right? So all of that multiplied through just a dot product of those two vectors. We see that the score that comes out is -3. And then when we put that through the sigmoid, that's telling us that with the current setting of weights, this classifier thinks that you have probability of class 1 of 0.0474. So in other words, with this setting of weights, this classifier is 95% certain that this is a class 0 example. And now what we're going to do is we're going to try to construct an adversarial example in the following sense, that we'd like to construct an X that is very similar to this X, but we'd like it to be classified as 1. So right now, the classifier thinks there's 95% chance of being class 0. We're going to try to flip that probability the other way around by slightly modifying X. And so if you have access to the weights, which in this case we do, and we know exactly what they are, you can in fact come up with a technique for actually constructing this adversarial X. And so how would we nudge X in every single dimension to screw up that classifier to make it predict the other class? For example, how it would change in the first column. What do we want to do with X in the first column in order to screw up the classifier? Way too many voices. Yes, so we want to make only tiny changes. The idea here is the adversarial example, we want it to be very close to X. want it to be very close to x, so we want to slightly depart from 2. You want to decrease x. You want to make x smaller, because then this thing will become smaller contribution. So you're going to get a smaller number than -2 in this dot product. So in fact, we can do this in every single column independently. So we want to decrease in here, we want to decrease in the second column, we want to slightly increase in the third column, and so on. So I can construct an adversarial example because I know what the weights are. And in particular, I'm going to only change it by 0.5 in every single dimension, but exactly in the correct way. And when I do that, what I find is when I do the dot product with my adversarial x, then since I've made tiny change in every single dimension, all of these changes exactly added up in a constructive way to give me suddenly a score of 2. And when you put that in the softmax, in the sigmoid, you come up to 88%. So I've slightly changed my x and I've blown up the probability. And intuitively, the reason this happened is because I was able to make a tiny change in every single dimension because I know what the weights are, and that allows me to blow up this score. And so think about, this is just a small example with 10 dimensions, but think about images which are 224 by 224, say. So there's 150,000 numbers, and the gradient tells me exactly how to change every single pixel in order to do arbitrary things downstream, like increase the probability of ostrich. And since I know what that gradient is on my image, I can nudge every single one of these 150,000 numbers in exactly the correct way by a tiny amount, and that allows me to completely blow up any class I want in a slightly depressing manner. And so that's roughly what's going on, and why this is kind of happening. And so I'll reinterpret this again in a bit. I just like to point out that, so basically the linear classifiers are a problem. They're very nice to use because they're easily trainable, and COMNETs work very well with them in the data manifold. But they're not very nice functions because you end up doing these very large dot products, and it's a lot of space to do small changes with large effects if you know exactly what changes to make. And so I'll come back to this point in a bit. I just like to show you that actually we can do very similar things and produce adversarial examples just with linear classifiers. So this has nothing to do with deep learning or with convolutional networks. We can do this with linear classifiers. So, so here we had these templates for CFAR10. We can also train linear classifiers in the case of ImageNet. So these are linear classifiers, templates that we're familiar with for, say, pizza or for daisies or for plates and so on. Okay. So we're just doing linear classification in ImageNet, and I'm going to construct adversarial examples. And so, for example, if I take a random noise pattern, and my classifiers think that this is 1% of being a bobsled, but basically very unconfident prediction here, I can take, since I know the weights for a goldfish classifier, I can add a tiny bit, I can mix in a tiny bit of goldfish weights, and I get an image that looks identical, although it's hard to see at this point, but this is a 100% goldfish, because I've changed every single pixel a tiny amount in exactly the right direction. I can do this also with real images, so I can take this image, I can add in a tiny bit of goldfish, and it turns out that I can make this much more likely goldfish. I can make the goldfish class most likely just by mixing in a tiny bit of those weights. Okay, and I can also do that, for example, with an actual goldfish, and I can make it a daisy, although this is not as clear. And so really what's going on here is, what's interesting is that some of these adversarial examples kind of came about first in the setting of COMNETs applied to images, and that's where we first noticed that this is happening. But in fact, this has nothing to do with COMNETs, because you can do it with linear classifiers. And in fact, like deep learning, the fact that we have all this wiggle that will allow us to maybe fix the problem, although I don't know exactly how we'll have to change the linear classifier, how we use linear functions might have to change. And also I wanted to make the point that this has nothing to do with images. We can do this in any other modality. So speech recognition is subject to the exact same problem because we're using these large networks made up of linear functions in between, and we can blow up these scores anyway. And so basically the way to think about this is, on the data manifold where we train our images with their specific statistical structure, everything works. But since these things are so high dimensional and we have the gradient, and this gradient, by the way, is like the optimal way of, the gradient tells you the optimal way of screwing up whatever you like, and you're computing it with this dynamic programming, which is really backpropagation, is a dynamic programming way of figuring out how to change your image in the optimal way to do anything you like downstream. And so in these high dimensional spaces, we can just get the precisely correct direction, and we just make small steps in it, and we can kind of get to arbitrary results once we actually meddle with the low-level statistical structure of those images. And so that's kind of what's going on, and we need to find a way to fix it. And right now, there aren't very good answers to it, I think, but it's a subject of research, area of subject. Good?
I mean, could you, after you have a fairly well-trained network, do some data augmentation, take these perturbed examples, feed them back in?
Yeah, so people have investigated a whole bunch of kind of simple fixes to this. So one example is if we don't just classify a single image, but we actually do many crops and we classify all those, you become more resistant to some of this for sure. But for example, some people have tried simple ways of fixing it. Like for example, I train my ComNet, I generate an adversarial example, and then I can add it into my training data as this is like a negative class or something like that. And I keep repeating this, and it turns out that you can always find more adversarial examples. Like it doesn't actually end up working very well. And so there's a few things that people have played with, which unfortunately I don't have time to go into by the end of this lecture. But basically small hacks that people have tried, and nothing so far is like very convincingly working. Something that is working is taking out the linear functions and trying different things. And so you become much more robust to the adversarial stuff, but then your classifiers don't work as well as they used to. And so there's some stuff like that, some trade-offs. Any? Go ahead.
Why is this a big problem? Because I don't see how these pictures would come up naturally anyway.
So why is this a big problem? Maybe one. So first of all, it's very depressing and kind of confusing. So that's a problem by itself. But in practice, maybe why it's a problem. For example, we found that these adversarial examples, in fact, they're not just a function of a particular ComNet, but they kind of transfer from one ComNet to another. Another one that was trained completely separately on different, like even data or so. So something on the low-level structure of that we're messing with images here is kind of screwing up ComNets all over the place. And so adversarial examples in one domain are likely to be adversarial in a different ComNet. And so maybe, for example, all of the companies are working with ComNets right now and analyzing your pictures with them. Like, you don't actually want people to be able to mess with your processing, maybe. I don't know. That's one example. Or I can maybe take my image and I can convince. So I know that this will go into Google and they'll analyze it with their ComNets. And I can make my image adversarial on my ComNets to be whatever I want. And then maybe I upload it and there's some chance that the same thing will carry over. And so maybe there's some repercussions to this, but I haven't fully thought it through. But I think it's definitely worrying. Go ahead.
Could you maybe show an image to a self-driving car that has...
Yeah, so that's a good example. I don't think that would work, right? Because this is like you're really meddling with the precise pixels that go into the ComNet. Like if you just show it with the camera, you don't have these weird statistical patterns. So I doubt that would work. If someone wants to do that for a project, by the way, if the adversarial examples carry over to like pictures of it, that would be really cool. I doubt that would work. Go ahead.
What about face recognition? Like logging in computers and things like that.
Oh, I see. That's a very interesting example. Face recognition. So I can make an adversarial example to be anyone I want, and then. Yeah, but again, you would have to show that. Yeah. So I should say that these examples don't just transfer right away. There's like a small chance, higher than you'd think by chance, that they do transfer, which is slightly worrying. Go ahead.
Is it really fixable in the sense that it kind of is like a case of curse of dimensionality because they're like these images are kind of out of sample, no?
Yeah, so the images are very out of sample, as you mentioned, and you still wouldn't like this property to hold true. Like, why can't you still recognize if you can recognize the school bus, you'd like to think that the ComNet should as well. I think but we do have to change our training process or something about it, and it's not clear right now like what to do.
Yeah, maybe add a lot of noise and say this is class of non-picture or something.
Yeah. Anyway, so since it's 419, I'd just like to summarize that backdropping to the image is a very powerful technique, and we saw many ways that this can be used for understanding, for segmenting, kind of, for inverting, for fun, and for confusion and chaos, definitely as well. And so next lecture, we're going to go into recurrent neural networks, recurrent neural network language models, and image captioning and stuff like that, so that should be fun. It is 4:20, so I'll end the class lecture here, but you can come.